What's up, everyone? The topic that I'm going to talk about today is successive interference cancellation. This is really an important topic these days, especially after the arrival of 5G in NOMA. SIC is often getting used. So if you're stumbling into any paper for 5G, then if you find out this term and search it on the internet, the first thing that comes out is a lot of theories, not many useful explanations, and also not many mathematical backgrounds that are easily explained for the understanding of this term. So today I'm going to put an effort to make it a very easy understanding for you. So let's do that. Let's look at the uplink of a communication system, a mobile communication system, for example, where we have two users. Their signals can be represented as Z is equal to M1 plus M2 plus N. Here, N is represented as noise, and M1 is for user 1 and M2 for user 2. And N is, as I said, is noise. It is additive white Gaussian noise. And N is complex Gaussian noise. You can say that too. Sometimes we say it as complex normal. So N is complex normal. And the users are transmitting with certain power. So power 1 for user 1 and power 2 for user 2. So power 1 for user 1 and power 2 for user 2. Our target, let's say, for example, is to get transmissions at the receiving end and decode that successfully. One way to do that would be divide the resources in an orthogonal way. So we can do either OFDM or TDMA. Let's look at the examples of those two. Our x-axis is our frequency, and let's do this. In the frequency domain, we could divide the frequency into subchannels and allocate certain numbers of subchannels to user 1 and a certain number of subchannels to user 2. So which is like this: M1 for user 1 and M2 for user 2. And if you're talking about like TDMA, so in the time domain, we can write like this way. So this slot is for user 1, this slot is for user 2, again this slot is for user 1, and this slot is for user 2, and it goes on. This is time division multiple access. And now let's look at the resources from capacity point of view. If we are giving the full resource to user 1, and if user 2 is not transmitting with any kind of power, then we can write it this way. R1, the rate of transmission for user 1 is log base 2 1 plus P1 and N0. The rate of user 1 will be up to this. This is called Shannon's capacity. If you're not aware of that, you can search on the internet, or I might plan to make a video of that term too. So this means up to this rate, we can transmit with completely zero errors. So in this part, we can see the P1 here is it denotes the power 1 for user 1. This P1 is power 1 for user 1, and N0 is the noise. This N0 is the noise. This same scenario, it holds for user 2 also. The scenario, what kind of scenario? Like as I mentioned, that if we are giving the full resource to user 1, and if user 2 is not transmitting with any power, and in this case now let's think it in a reverse way, that we are giving the full power, full resources to user 2, and user 1 is not transmitting with any kind of power. So in that case, we can write the rate of transmission for user 2 is log base 2 1 plus P2 n naught. So, okay, so one thing is like why we're using base 2, because we're dealing with bits. There is a third constraint, which is the sum rate constraint. User 1 and user 2 are sending independent signals. Let's assume that. So based on that, we can write R1 plus R2 is less than log base 2 1 plus P1 plus P2 and sorry, I made a mistake. This should be here. So this is like P1 and plus 2, P1 plus P2 is a single transmitter with combined power. This P1 and P2. Now we have some upper bounds from the equations. Let's plot R1 in X and R2 in Y axis. We will use this one here. This portion for the graph, so that we'll edit one single graph again and again to give you the full view. So we'll use this portion for that. Let's plot it. It will be like this is R1 and this is R2. If user 2 does not transmit with any power at all, we will be able to receive R1 max. And let's say R1 max is this point. R1 max. And if user 1 does not transmit with any power at all, we will be able to receive R2 max. And let's say this point is R2 max. Let's assume that transmission powers are fixed. We cannot increase them. Also, let us assume that we have divided our time slot in TDMA equally to 2 users. So we are going to turn on user 1 for half of the time and turn on user 2 for half of the time. For example, if this one is a whole slot, this one is slot 1, so we are going to turn on user 1 for a certain time and user 2 for a certain time. This leads us to a point in the graph which can be, for example, here. So under the assumption that the power per subchannel is fixed, then we can get a similar curve for this OFDM2. The part that I was talking about was TDMA. And if our assumption regarding the power is same per subchannel in OFDM, then this point can be also OFDM2. So the question is, can we get a bigger combined rate that will either exceed R1 max or R2 max? So we have come to this point that like this R1 max is the highest transmission rate. This R1 max is the highest transmission rate for user 1, and this R2 max is the highest transmission rate for user 2. So the point is, can we get a bigger combined rate? If we combine R1 and R2, can we get a bigger combined rate that will either go past this R1 max or either go past this R2 max? That's possible, and we're going to see that in coming few minutes. So let's make our graph again. I think for the next steps, you're going to need the graph more. So let's make it clearer. Now, let's transmit at the same time. So previous discussions were like this. We were like transmitting user 1 from like with full power and no transmission from user 2, and we are transmitting from user 2, and we are not transmitting from user 1 with any kind of power. And now what we are going to do is transmit with full power at the same time. This will definitely cause interference with one another, like interference between the users. From what we know from capacity is user 1 and user 2 is going to interfere, but they are not going to do it in a very disruptive way. We're going to get something. Certainly we're going to get something. So if user 1 and user 2, they are transmitting at the same time, let's look at their transmission equations for that. So user 1 and user 2, they are transmitting at the same time. So the rate for user 2 will be, let's name that as K2 is equal to log 2 1 plus P2 divided by P1 plus N naught. This equation is kind of similar to the equations, the limits, upper limits that we have seen before. This is the rate that we can achieve for user 2, this rate, when both of them are transmitting at the same time. And here, the only difference is like the noise level has gone higher. Now the P1 term has got added with the noise. This value is definitely going to be lower than the R2 max. The same equation it goes for user 1, like the rate for user 1 if we are transmitting at the same time, and that we can write as K1 is equal to log 2 1 plus P1, and this time P2 plus N naught. The interesting fact is that this is at this point where the part of SIC comes. Let's elaborate a little bit. So according to the definition, if you can receive from user 2 at K2 rate, this is going to be less, at K2 rate, it means that you are getting that data with 0 errors that we can perceive from the capacity formula that I showed earlier. Let's assume we have zero error for user 2 and we have completely decoded the signal from M2. So our equation was Z is equal to M1 plus M2 plus N. So if we are transmitting at this K2 rate, then we can detect the signal of the user 2. And if we can detect the user of the signal 2, then of course we can subtract M2. And in that case, our equation is going to be M1 plus N. Since we have decoded M2 successfully, after and we have subtracted that, we have user 1 now and the noise. We don't have user 2 anymore. So the capacity for that is what? Is this. R1 is log base 2 plus P1 N naught. Oops, sorry. I have made a mistake. R1 is less than log base 2, 1 plus P1 divided by N naught. So does this look similar or familiar? Yes, it does. I think it should. This and this is similar, which is R1 max. So for our user 2, if you're following this, then this is going to be less than R2 max, and for user 1 we're getting R1 max. So if we draw the graph again, this is R1, this is R2, here is R1 max, and here is R2 max, and the K2 point is less than R1 max, R2 max, so this is gonna lie here, and for user 1 we have got R1 as this, so this is going to be R1 max. So in that case, okay, let's get it. Previously our graph was like this also. So this point and this point. And the same thing it goes for for the other user too. So if we are doing it for user 1, then what happens is we first decode user 1's rate. Then our equation for user 1, it becomes K1 is less than log 2, 1 plus P1 divided by P2 plus N naught. So in that case, any signal in this boundary is going to be decoded perfectly for user 1. And if we know user 1, then as we can cancel out user 1, and we get only z equals m2 plus n. So in that case, this is nothing but the equation that is over here, which leads us to R2 max. So in that case, for R1, if the value lies in here for K1, then we are talking about R2 max, then this is going to be our graph. So this means we can compromise with the rate for any user and still send the other user at maximum rate. So our SIC is nothing but this. If we can lower our rate for a user and decode it correctly, we can cancel the interference through the subtraction and send at full rate for another user. Hope this video helps you to understand. Thank you.